Exploring the Solar System, Part 2, how we explore the solar system with spacecraft. So we'll be asking the question, how do we get there from here? What do we do when we get there? And given that we're often interested in images, scientists want more than just images, but everybody else would like to see images of the planets we visit. So how do we get the images back? And again, where do we go from here? I thought it might be useful just to recap, not in any detail, how many spacecraft we've sent up. And I thought to myself, I wonder how many spacecraft we have sent out. And I thought it's got to be dozens. And then I counted them all, and it's actually rather more than I thought. It's well over 200. I think it's over 250, including the most recent. I'm sure you can't read this, but the last one there is Europa Clipper, which was sent up a couple of months ago on the way to Jupiter's moon, Europa. So we have been sending spacecraft out from Earth for many decades, and we are approaching something like 300 spacecraft being sent to various objects, whether they be the moon or the planets or other rocks in the asteroid belt or beyond. We talked before about getting to Mars. If that is the orbit of the Earth around the Sun, this is not to scale, but I've just exaggerated. If we want to get to Mars, one of the easiest ways of getting from Earth to Mars is to follow an orbit shown there in blue. If I take away the red and the green, the orbit is actually an ellipse. Isaac Newton told us that that's how planets go around the Sun, in either circles or ellipses, and it turns out that's the easiest way of getting from Earth to Mars. It's one of the simplest routes we can take. Once you've launched from Earth, you can switch your rocket off and coast all the way on that blue line to Mars. But if you want to go further afield, it starts getting tricky. Back in the 1960s, it was realized that you can use a slingshot. You can go past Jupiter and you can get it to slingshot you even faster towards the outer solar system. And that was done in the 1970s to try and get not just to Jupiter, but to use Jupiter to slingshot you further out to, for instance, visit Saturn in the case of Voyager 1, launched in the late 1970s. So it just so happens that back in the 70s, the planets were lined up in such a way that it was figured that, yes, we can probably send something to Jupiter and then slingshot to Saturn, and if we do it right, we can use Saturn to slingshot us to Uranus, and we can use Uranus to slingshot us to Neptune. That's why in the 1970s, the Voyager program, including this one, Voyager 2, was set up, that launched from Earth, was a slingshot from Jupiter, who threw it onto Saturn, which then slingshotted it onto Uranus and then onto Neptune, and then out of the solar system. Both Voyagers are now moving so fast because of this slingshot maneuver, which is properly called a gravity assist, but everybody calls it a slingshot. The slingshot gave these craft so much speed, they are now comfortably leaving the solar system. There's no way Sun's gravity can ever pull them back again. They are moving so fast. So it'll take a long time, but eventually Voyagers and other probes like Pioneers from the 1970s are going to find their way to other solar systems. It'll be thousands of years before they get there because the distance between stars is so great, but they will eventually get there. So the idea of slingshotting has made the outer solar system a little closer to home. Still takes quite a while, but slingshot makes them go faster, which means you need less fuel to get there, and you actually get there faster. Still takes quite a few years to get from here to Jupiter or Saturn, but it can be done much more economically. Here's an object that was photographed some time ago. Anybody recognize which particular body this is? If I tell you which spacecraft took it, you will instantly know. This was taken by Luna 3, therefore. This is actually the far side of the moon. It's not the familiar face that we see, which is the near side. Until this point, we didn't know what the far side of the moon actually looked like, because the moon always has one face pointing towards the Earth. We can clean that up a little bit by removing some of the noise. But what's amazing is not the fact that this is the first picture of the far side of the moon, it was the technology that allowed us to do that. Not only do we have to put a spacecraft on top of a rocket and get it to go onto the other side of the moon, but when we think of the technology, this is the 1950s. This is before digital cameras. We take it for granted these days that everybody has got a digital camera in their phone, and if you want to take a picture, you just point, click, done, you've got a picture. That wasn't the case in the 1950s. Here they had film, yes, film, and they had film in the space probe which was exposed and then developed chemically and fixed and dried and then scanned by a sort of flying spot, and then the intensity of the light was transmitted back to Earth where they reconstructed the image, effectively like a big fax machine. So it was chemically developed and then scanned and then transmitted back to Earth. For comparison, there's a picture taken much more recently of the far side of the moon, taken with Lunar Reconnaissance Orbiter, one of the NASA probes. And although the quality is better, notice that all the features are in the right place. So this definitely worked. It was tricky, it was difficult, it was technically challenging, but it did give us an accurate indication, albeit low resolution, of what the far side of the moon actually looked like. When we move into the 1960s, we have digital cameras. The world's first digital camera was not in an iPhone, no, it was on Mariner 4. The world's first digital camera. Digital cameras were made for space probes, and as a spin-off, we all got digital cameras in either compact cameras or ultimately in phones. But the digital camera on Mariner 4 stored all of the data on tape, and then once it had done the flyby of Mars, the tape was rewound, and then the tape was read, and that information was then transmitted back to Earth so we could generate an image of Mars. So the first digital image was effectively one of the Martian surface, and this is the mid-1960s. We have now effectively visited everybody in the solar system, not, let me rephrase that, every major body in the solar system. We visited all the planets, and we visited some asteroids and some dwarf planets. We have now effectively explored all of our solar system. So let me just pick out one example, because again, in a short talk, we can't possibly cover everything that's been done. But Cassini was a mission that was sent to Saturn to look at Saturn's rings, and look at some of Saturn's moons. It was sent there in the mid-noughties, and it spent years and years and years orbiting Saturn, getting as much data as it could before it was finally crashed into Saturn in 2017. Why did they crash it into Saturn? Because, like Jupiter, Saturn has got a lot of very interesting moons, and those moons might conceivably harbor life, and they did not want the Cassini mission to accidentally crash land on a moon and possibly contaminate the moon. So they deliberately crashed it into Saturn, which, as far as we know, has no possibility of harboring life. To give you an idea of scale, on the bottom right there, there's a human standing next to the Cassini space probe. There's a whole load of numbers there, which I won't go through, but some of them are pretty amazing. The fact that this space probe traveled through 5 billion miles on its way out and then orbiting Saturn to take its data. It generated huge amounts of data. Millions of commands were sent and received back from the mission itself. And it took a total of 500,000 images of Saturn and Saturn's rings and Saturn's moons. As seen from the Hubble Space Telescope from here on Earth, that's what Saturn looks like. We get some lovely detail from the Hubble Space Telescope. But if we look in even more detail, because spacecraft simply are much closer, they will of course see much more detail. So when we look at the detail that Cassini sees from a relatively short distance away, we see a phenomenal amount of detail in the ring system, and we see things that we might not have seen from Earth. It looks more like a long playing record, for those that remember long playing records, than it does a ring system. We can't resolve it here, but what we're looking at is trillions of tiny ice particles, all independently orbiting around Saturn. It's a very flat system. The ring system might be 250,000 kilometers across, but it's thought to be only a few meters thick. It is basically the thinnest thing relative to its size in the solar system. When the sun is at the right angle, when you catch the rings that are level with the sunlight comes in at a glancing angle, and it reveals the fact that some of these things are actually bumps because you can see their shadows. When the sun is really low, these shadows are cast across the rings. And we get an idea that these bumps are perhaps kilometers or so in height. So there are mountains, if you like, in the ring system. Most of the rings are dead flat, but there are these mountains. Trying to understand the dynamics of the ring system is ongoing. And one thing you can't do from Earth is do this and fly into Saturn's shadow and look at Saturn backlit. Of course, from Earth, we can only see Saturn lit from the sun, and we are fairly close to the sun compared to the distance to Saturn, so we see Saturn sunlit. But a spacecraft can fly into the shadow and see Saturn backlit, so some light is coming through the atmosphere, and the rings are being backlit. So again, we get more information about what these ring particles are by seeing how they scatter sunlight. And occasionally we pick up a few moons in here, so-called shepherd moons, which are helping the structure of the ring system. One extra spacecraft was bolted onto the side of Cassini called Huygens. That hitched a lift, if you like, with Cassini, and then it broke away and was programmed to enter the moon Titan. Titan is one of the biggest moons in the solar system, and it has what appears to be a very thick atmosphere, mainly methane. But as the Huygens lander actually went through Titan's atmosphere, it took images as it went. So we weren't too sure what we were going to find. The atmosphere is so thick we can't really see the surface of Titan, but the lander, as it came in, told us that this is definitely a moon which is a world in its own right. As you come in, you can quite definitely see this is a moon which has mountains. It appears to have rivers and lakes, probably not water because this is so far away from the sun. This is probably methane rivers and methane lakes. But still, it's a world with a rich geology, if that's the right word to use for another world. It definitely has mountains and lakes and is well worth exploring in more detail. In 2016, Juno was sent to Jupiter. Again, takes a little while to get there. Again, some huge numbers, billions of miles traveled. I don't know how many images were taken, 20,000 images, millions of commands, in order to get information about Jupiter and Jupiter's moons. This is sort of what Jupiter looks like from Earth. We can sort of unwrap it and say, well, it seems to have cloud systems. It has different colors. We see white and reds and browns. That's to do with different elements that are in Jupiter's atmosphere. The white is the cloud tops. That's probably ammonia. The dark colors, like the reds, are probably coming, the reds and the browns are probably coming from other elements like phosphorus and sulfur. And again, trying to understand the cloud systems, the weather systems on Jupiter, helps us try and understand weather systems on other planets. Juno was designed to go into orbit and swoop down over the surface of Jupiter. And as it came, it swoops down and you get a real close-up view of the planet. You can see the chaotic storm systems. You see occasional flashes of light. That's lightning in the storm systems on Jupiter. As Juno flies close to the surface, we get incredible close-up detail, and then it flies away as it's going in a rather eccentric orbit. It goes a long way from Jupiter and then flies close, then a long way from Jupiter and then flies close. It has to go in a rather odd orbit because there's a very high radiation area around Jupiter and it can't stay in a high radiation zone for too long. But the amount of detail from the Juno cameras is absolutely phenomenal. You can argue that a picture like this you could study for years and pick out the detail of what is actually happening as a dynamic weather system. Why do we get these structures? Why is it bluer at the poles compared to around the equator? What are these white spots? Jupiter has a large red spot, which is a storm. Why has that storm lasted for hundreds of years? Why hasn't it dissipated? Some of these systems, you look at this and it looks just like an impressionist painting or a watercolor left out in the rain. The actual aesthetics of these images is truly amazing. It's thought that this dark spot in the middle there is actually a vortex, is a funnel, if you like, leading down to deeper parts of the Jovian atmosphere. And this particular image was taken just a few thousand kilometers skimming over the surface of Jupiter. This is a video showing you some of the complexity of the storm systems. This is a video taken over a few hours showing just how complex the motion of the cloud tops on Jupiter are. Now, the solar system, of course, is not just the Sun and 8 planets. Even this solar system on the front bench here is planets and a few other rocks as well. New Horizons space probe, for instance, is now exploring beyond Pluto. It was sent out to look at Pluto and its moon Charon. It did that. It flew by. In a few hours, it took all the images that it needed, which is then transmitted back to Earth. And New Horizons probe is now flying through the Kuiper belt, the belt of icy particles beyond Pluto. And we don't really know what's out there, but we're trying to get New Horizons to look when it passes some of these interesting objects. Every once in a while, New Horizons gets close to one of these Kuiper belt objects. We're trying to direct its cameras to get as much information of what these Kuiper belt objects are. Some of the larger ones we've managed to image with big telescopes, but there are trillions of objects out there. Let's see how many we can image. And in addition to all of these icy particles, there are also hundreds of moons. Earth has 1 moon, Mars has 2 moons, but if you add up all the moons in the solar system, there are over 300 of them, and they are all worlds in their own right. Some are large enough to have atmospheres, some are spherical, like our moon, some of them appear to be more like potatoes, and others seem to be more like, I don't know, the Death Star from Star Wars. If we look at the moons of Jupiter, Jupiter has 4 large moons. One of them is very volcanic. The one closest to Jupiter is getting stretched and squeezed and seems to be a volcanic world. But the other 3 are interesting because they appear to be ice worlds. The one below there is Titan, the one we saw Huygens moving through into the atmosphere. But these 3 are the focus of recent attention because we are getting evidence from all the space probes that have visited them before that these icy worlds, they may be ice on the surface, but there appears to be water underneath. Whenever you have water, we think you have the possibility of life. If you have water and the right mixture of chemicals, then life perhaps will find a way. There's actually more water on these moons than there is on the entirety of Earth. Even the entire Pacific Ocean and the Atlantic Ocean are dwarfed by the amount of water held by these moons. So there are spacecraft on their way. JUICE was launched a couple of years ago. Europa Clipper was launched just a few months ago. JUICE is an ESA mission. Europa Clipper is a NASA mission. These are on the way to Jupiter explicitly to try and find out what's going on with these moons. If they do have liquid water, why do they have liquid water? These are a long way from the sun. Something must be keeping these objects warm so that some of the ice has melted and formed a liquid. What's going on, and what do we need to do to explore these water and ice worlds? Up till now, all of the spacecraft we've sent out, we've got everything back from these spacecraft by radio waves. Basically, a radio transmitter on the spacecraft, a radio transmitter, a big dish on the spacecraft, sends radio waves back to the Earth, and a big radio dish on the ground, like Jodrell Bank Observatory or other observatories around the world, they pick it up. That's how it's been done for the last 50 years or more. But there are now tests being done where they're saying, well, why should we use radio? If we use lasers, it could be faster. Lasers are capable of carrying a huge amount of information. And therefore, if we send a laser beam back from the spacecraft rather than a radio signal, perhaps we can get much better data rates. Radio signals might transmit information at only a few bits per second or a few thousand bits per second. In principle, lasers are capable of much higher data rates, and so they would be picked up by an optical telescope like the Hale telescope here rather than by a radio dish. To test this, they sent a probe up to an asteroid called Psyche, and they said, let's just see, what if we send a laser signal back? What are they going to transmit? Well, Psyche isn't a very interesting object to photograph, so they said, what's the biggest amount of data we can send back? What do most people spend their time looking at on YouTube? They spend their time looking at cat videos. So they thought, if we're putting this on a laser beam, let's send a video of a cat chasing a laser beam. So this is what they sent back from the Psyche spacecraft. It's a high-resolution, high-definition video, and at a distance of 50 million kilometers, it was sent at a data rate of 260 megabits per second. Some people don't even get that in their broadband at home. You can't get a signal from 10 miles away at that sort of rate, but this was taken effectively even from another planet. You still get many megabytes or megabits per second of transmission. Substantially faster, thousands of times faster than are capable with radio transmissions. So it does work. So maybe this is the future. Instead of having to wait days and days and days to get information sent back from distant planets, maybe if we use lasers, we'll be able to get that data much, much, much faster, and perhaps images at much higher resolution and videos at much higher resolution. So Cassini is no more. That was crashed into Saturn a few years ago. But Bepi Colombo is on its way to Mercury. I've said New Horizons is on its way out of the solar system. Juno is looking at Jupiter, and I've said that the JUICE and the Europa Clipper missions are on their way to the icy moons. So there's lots of things happening now, and there's lots of things that are going to be happening in the next few years. If you explore any of those web links, you'll find NASA and ESA and other space agencies have enormous amounts of information telling you what they're doing and why. Thank you all very much.